Hello all. I'm happy to welcome you all back to this lecture series on process heat transfer. So in today's lecture series, we are going to see about the energy balance for a heat exchanger. So basically, heat exchanger is a device that helps to transfer heat between two fluids, one of which will be a hot fluid and another one will be a cold fluid. So when I say this, you normally might get a question. So what is the need to go for energy balance for a heat exchanger? So let us imagine we have a heat exchanger. At times we might know the inlet and outlet temperature of the cold fluid, and sometimes we might not know the outlet temperature of the hot fluid with the inlet temperature of the cold fluid being given. At such cases, and also during the design and operation of heat exchangers, for example, at times I do not know what might be the flow rate of my hot fluid and flow rate of the cold fluid, at what flow rate the fluid has to be sent inside the heat exchanger so that the operation will be efficient. And during such questions of finding out the heat duty of the heat exchanger, so during all this process, energy balance plays a very important role. So basically this energy balance works on conservation of energy, that is the heat that is being lost by the hot fluid during the process of flowing into the heat exchanger is actually gained by the cold fluid, right? Whatever the heat that hot fluid has with it is actually given to the cold fluid by the hot fluid, which means it is being transferred. Here the heat is being transferred. That is the important principle behind this heat exchangers. So please look into the slide where we have a heat exchanger. We can look into the slide and we can find that the hot fluid and the cold fluid are entering into the heat exchangers in the opposite direction. Please look into the slide. We can see that the hot fluid is entering from the right side, whereas the cold fluid is entering from the left side, which means we call it as a counter current direction, right? In case if it is a parallel flow or co-current flow, then both the hot fluid and the cold fluid will be entering into the heat exchanger in the same direction. So now, before getting into the derivation or equations for this energy balance, let us be clear with the terms. So mH be the mass flow rate of the hot fluid, mC be the mass flow rate of cold fluid, capital H C1 and capital H C2 be the enthalpy of cold fluid at the inlet and outlet, where capital H H1 and capital H H2 are the enthalpy of the hot fluid at the inlet and outlet. Whereas we also have other terms like Q, and QC and QH are the rate of heat addition to the cold fluid and the hot fluid respectively. So please look into the equations. I have given you that QC is equal to minus QH. We know that Q is the rate of heat, right? So rate of heat transfer is normally given by the symbol Q. When I say C, it represents the cold fluid, and when I say H, it always represents the hot fluid. As I told you before, the heat lost by the the hot fluid is actually gained by the cold fluid. So here I have given a negative symbol for the hot fluid. Why? Because the hot fluid is actually leaving its heat, which is actually gained by the cold fluid. So here we normally give a negative symbol for the hot fluid because heat is lost by the hot fluid and the heat is gained by the cold fluid. So normally we can write the same Q in terms of mass flow rate and enthalpies, right? So for the cold fluid we can write it like mass flow rate of the cold fluid into enthalpy of the cold fluid at the inlet and outlet. Similarly, for the hot fluid, we can write it as mass flow rate of the hot fluid into enthalpy difference of the hot fluid at the inlet and outlet. Now, from here on, we might have two different cases. One, the first case where only sensible heat of the hot fluid is being transferred on second hand, where the latent heat also gets transferred. So there might be two cases. Let us imagine the first case. Please look into the slides. We can see that I have given you the equation that mCp delta T. So in this case, where I imagine only sensible heat is being transferred. Okay, let us have a heat exchanger where the hot fluid is flowing inside in one direction and the cold fluid is flowing in the opposite direction, just like what I have given in the previous image, right? So now, as the hot fluid passes through the heat exchanger, let us imagine there is no phase change that is occurring in the hot fluid side. Imagine the hot fluid is entering into the heat exchanger in the liquid phase, and while leaving the heat exchanger also, it remains in the same liquid phase, which means only the sensible heat of the hot fluid is being transferred to the cold fluid. Okay, so in this case we know that whenever the sensible heat is involved, we go for the equation mcp delta t, where m is mass flow rate of the fluid, cp is the specific heat, and delta t is the temperature difference at inlet and outlet. So here, as I told before, it is basically the conservation of energy. So obviously the heat that is lost by the hot fluid should be gained by the cold fluid. So mcp delta t of hot fluid should be equal to mcp delta t of the cold fluid, right? On the other hand, let us imagine the latent heat is being transferred, which means the hot fluid which is entering into the heat exchanger in the liquid phase, right? When it reaches the end of the heat exchanger, it becomes a vapor, which means not only the sensible heat of the hot fluid is being transferred, the latent heat is also transferred. In this case, we go for m into lambda. So lambda is known as latent heat of vaporization, where m is the mass flow rate. So let us consider only the hot fluid side. You can look into the equation I have given you. mh, that is mass flow rate of the hot fluid, into lambda, that is the latent heat of vaporization, should be equal to mcp delta t of the cold fluid. The same law of conservation, that heat that is lost by the hot fluid is actually gained by the cold fluid, is given here. One important difference is that, as I told before, the hot fluid that is entering the heat exchanger in liquid phase, as it reaches the end of the heat exchanger, it turns into vapor phase by giving all of its latent heat to the cold fluid. So in this case, there is a phase change, and that is the reason why we are going for m lambda. And it is important to note that this m lambda is applicable only for the hot fluid, because only the hot fluid is going some phase change, where it is transferred from liquid phase to the vapor phase. On the other hand, the cold fluid remains in the same liquid phase. That is the reason why on the right hand side, for the cold fluid, the same mcp delta t equations is used. So when we try to solve problems related to heat exchangers, it is important to know which equation should be used, whether we have to go for this m lambda or mcp delta t. And for this, we have to read the question carefully, where we have to check whether the inlet hot fluid is transferring, it is undergoing any phase change or not. So it is very important to note this point. So as I told before, this energy balance equation is very important during both design and operation of heat exchangers. So this is the basic energy balance equation for any heat exchanger. So next we are going to see about this concept of log mean temperature difference. So many of you might have a question, right? Why we are going for this log mean temperature difference? So basically we can also have a mean temperature. What, for example, we have 5 different temperatures and we want to find out a mean temperature. What we normally do, we just take it like T1 plus T2 plus T3 plus T4 plus T5 divided by 5, right? But when we take a heat exchanger, why we are going for a different concept like logarithmic mean temperature difference? So let me explain you that. It is, imagine you have a heat exchanger. The hot fluid is entering in one side and the cold fluid is entering from the opposite side, or on the same side, you can imagine. So as the fluid passes into the heat exchanger, continuous heat transfer is going to take place, and the temperature of the fluid will be varying at each and every point inside the heat exchanger, right? At each and every point throughout the length of the heat exchanger, the temperature of both the hot fluid and also the cold fluid is going to vary continuously. So in this case, if we go for a mean temperature like usual, for example, where we just go like hot fluid temperature, inlet temperature plus hot fluid outlet temperature divided by 2, which is a normal mean, where we go like T1 plus T2 divided by 2, is not going to give us the correct temperature difference, and this might in turn will give us a wrong Q value, that is wrong heat transfer rate. So this is the importance of logarithmic mean temperature difference. And when we speak about this delta T LMTD, this value highly depends based on the type of flow. For example, sometimes a fluid might be flowing in the parallel direction, and some fluid might be flowing in the countercurrent direction, right? So for example, when we have two fluids flowing in the same direction, then in this case imagine we have a hot fluid and cold fluid. Both the fluids are entering into the heat exchanger from the same directions. Okay. In this case, the delta T LMTD will be given by delta T1 is equal to hot fluid inlet temperature minus cold fluid inlet temperature, since both the inlet are on the same side, where delta T2 is equal to hot fluid outlet temperature minus cold fluid outlet temperature. Why? Because both the outlets are also in the same direction. On the other hand, when we know that it is happening in a counter current direction, where the hot fluid will be entering from one direction and the cold fluid will be entering into the heat exchanger from opposite direction. So in this case, del T1 will be equal to hot fluid inlet temperature minus your cold fluid outlet temperature, because the inlet will be on one side and the outlet will be on the other side, whereas del T2 is equal to hot fluid outlet temperature minus cold fluid inlet temperature, because where you have the hot fluid outlet temperature, in the same direction you are going to have the cold fluids inlet temperature, and at the entry when we have the hot fluids inlet temperature, that is the same direction we are going to have the cold fluids outlet temperature. So when the direction changes, the delta T1 and delta T2 values will also be changing. So when we are trying to solve problems related to these heat exchangers, it is important to note down which direction is specified in the question. So by default, if it is not given, we know that the counter current direction is going to have good value of delta T LMTD, and it is going to have high temperature difference. So because of this, we know that Q is equal to directly proportional to this delta T LMTD, which is equal to U, that is overall heat transfer coefficient, into area of the heat exchanger into this delta T LMTD. Since Q is directly proportional to delta T LMTD, we know that as the temperature difference increases, obviously the rate of heat transfer is also going to increase. So you can have any kind of problem. For example, you can imagine any values of hot fluid inlet temperature and hot fluid outlet temperature and cold fluid inlet and outlet temperature. And if you go for this delta T LMTD calculation for this co-current and counter current, obviously counter current is going to give you high delta T LMTD value. Since this rate of heat transfer is directly proportional to delta T LMTD, it is better to go for counter current direction. So thank you for watching this video. An upcoming video will come up with next new topics. Thank you so much for watching. Thank you.